SwayamPrabha. Digital India. Educated India.
Three, four classes will be a little bit more about machine learning rather than inverse heat transfer for machine learning, and then we will apply it. So I'll just roughly show you today. Today's class will be mostly introductory in nature to what topics we'll be covering, and what I'll be doing after that. I'll also try and give you some brief short questions in the middle, as Professor Balaji was doing earlier, but currently I'm going to do it online, and then as an online quiz kind of thing. This is not graded. Then apart from that, we'll of course do the usual assignment tests, etc., as we go forward. So I'll try to keep it as hands-on as possible as we proceed, because the topic can get reasonably theoretical. Let me share my screen. As always, please feel free to sort of interrupt me if you have any questions, etc. I will cut off my video just so as to preserve bandwidth. Sometimes there is an issue here I have noticed in other meetings. I'm just cutting off as I'm showing my slides. I'm going to stop the video. Yeah, but please feel free to comment and stop me in case something is unclear. So what we'll be doing, as I said in the next few classes, is inverse methods in heat transfer, but using some machine learning techniques. So today's class is basically why do we include machine learning as one of the topics within heat transfer. So of course, in general, whenever we study heat transfer, we have one of three primary goals as an engineering study. We can study it theoretically, but engineering study of heat transfer comes with one of three possible goals. One is to try and in any application increase heat transfer. In other cases, you want to decrease the heat transfer. And finally, in some cases, you simply want to control the temperature. Now, how do we study this? So if you want to increase the heat transfer, you need to find out the temperature and the heat transfer rate. This is basically what all of you would have done throughout our heat transfer course, which all of you would have taken earlier. So we have three approaches. The analytical approach, this is primarily what we did in our classes, so start with the differential equations, solve them, etc., etc. And of course, historically, it was studied experimentally. You measure heat transfer. You can either directly measure heat transfer or measure the temperature field, and through that you can measure the heat transfer, etc., etc. Finally, nowadays, a very popular option is to use computational methods. Some of you might have done this small projects using this ANSYS Fluent or some other package. You can solve the governing equation at the discrete level. So instead of solving it analytically, which is at the continuous level, that is, you get a single function throughout, you can solve the governing equation at the discrete level, which means I give you a set of points. And we'll see this later on once again when we do what are known as physics-informed neural networks. So you try and solve for the temperature here or the heat transfer right at the place that you want. So what makes it possible is this set of techniques called within computational fluid dynamics, and some of you would have done a course for this. In any case, traditionally we use one of these three approaches. You use either an analytical approach or an experimental approach or a computational approach. Now, what you might notice, is that in none of these cases we explicitly use prior data. I'll just give you one example to clarify what I'm saying. So let's say you are doing a computational solution, and if you use the package in order to solve heat transfer for a particular let's say configuration, or let's say you are trying to find out the pressure and velocity distribution on an aircraft. Now, if I change the design of the aircraft a little bit, the only way for you to get the new flow field is to solve the governing equations again at the discrete level. You cannot reuse the fact that you know a nearby solution. That you cannot do. So this has been something that we have been doing sort of implicitly in prior studies, but explicitly there is no big package which still uses this. Okay. So let's come to moving from this kind of abstract study to actual engineering. So typically, we wish to understand the process of heat transfer. Again, we just wrote that it can be either analytical, experimental, or computational. But what does it mean to understand? We have seen in this course that you try and obtain a cause and effect relationship. That it means, what I mean by cause and effect relationship is that in case you have, let me just start the video. So in case you have something like a fin, and you know that temperature at these places or the external convection is going to cause a certain amount of heat transfer, you try and relate the external convective coefficient to the effect, which is basically the temperature within the fin or the heat transfer within the fin. Okay. But how do we get these relationships to control Q or T or understand the parameters of control? So basically what you try and do is you say my input is the convective heat transfer coefficient, my output is the net heat transfer, and there will be a connection in between which we call parameters. I'll make this clear in the next slide. So typically we have a lot of physical parameters in any problem. I will again and again use the example of our fin, because this is something that you have done a lot in this course. At least this simple example is sort of an orienting example. So if we use this example, you can kind of reorient yourself each time. So suppose I want to find out heat transfer within this fin, and let's say my Q here is the output of the problem. We can have multiple inputs of the problem. So the inputs of the problem could be spatial coordinates. I mean, where am I measuring the Q? Where did I take my thermocouples and measure temperature? At what time am I measuring? What's the thermal conductivity? What's the specific heat? What's the emissivity in case we have radiation in this problem? Okay. The flow around the fin, is it laminar or is it turbulent, etc., etc. So these are a large number of parameters. Okay. Now, when you have a lot of physical parameters, you would have seen this in your fluid mechanics course also. You want to obtain this relationship. Again, same thing. You can either do this through theory, you can either do this through experiment, or you can do this through computation. But there is a practical issue. Okay. The practical issue is that how many experiments will you do? How much theory will you do? So as I was saying, suppose we are trying to optimize. Those of you who have done an optimization course would know that you would have to do the forward run of the problem multiple times. By that I mean that for each shape, you will have to find out what the heat transfer is, and then you will have to iterate amongst many shapes. Okay. So in case this computation, okay, or this experiment is expensive, that is, you have to do a lot of work just in order to get one Q out of these input parameters, then making an optimization becomes extremely expensive in terms of computational time. For example, just to give you some motivation for what we'll be doing a little bit later, one of the automobile companies had come to us, me and some of my colleagues, to say that their typical design cycle for, let's say, HVAC within their car took close to a year and a half just to run these simulations. So if you keep your AC vent, etc., in a particular place in the car, which would give you optimal cooling. There are regulations for how you can place your HVAC inside a car, etc. So if you want to do that, what should be the shape of my fan, etc., etc. When you do something of that sort, it takes a lot of computational effort to keep on making small changes in the shape and trying to get the the output, especially if your flow is turbulent. So the question that arises is, if I have done the design for one sort of car, can I extrapolate the insights from here into another sort of car or another sort of geometry or another sort of situation? Okay, so all these are basically questions about reusing prior data. Okay. So here we come to a distinction between two different classes of models. One I am going to call a data-based model, not a database, but a data-based model versus a physics-based model. Okay. So you have been doing this kind of thing for quite some time in the course so far. We have causes which are the same as inputs, and you have effects which are the same as outputs, and we have some model in the middle. Okay, this model could be out of any origin. Okay, typically something, let's say there's a black box. Somehow I give all these inputs, the location, the time, the conductivity, and somehow I am getting out the desired output, which is the heat transfer. Okay, whether you are doing a forward model or an inverse model or inverse problem, you need a model. Okay, so this model says, how are my inputs related to my outputs? So far, okay, in all the cases so far, you have used a physics-based model. Okay, so for example, know that within a slab, the temperature will be linear. Okay, so we had a physics model. We had, for example, our heat transfer equation. We see d square t dx square equal to 0. Solve for the differential equation. You get a model which is linear, and then based on that, you can find out conductivity or whatever we wish to find. But the model that t is linear itself comes from physics. Okay. Another option is, suppose for some reason you don't know the physics. Okay, you can collect a lot of historical data. This is basically how, for example, if you see pipe flow, a lot of models for, how does a pipe pressure drop depend on friction. Even before we had any theory, a lot of models of theory for turbulence, a lot of models were basically based on data. That is, you collect a lot of historical or experimental data and you start figuring out patterns within this, patterns meaning mathematical patterns. Now, what all can data models do? This term is an important term. I'll be using this several times in this course. You can create surrogate models. A surrogate model is an approximate model. Okay, an approximate model in the sense that instead of giving the full scale physics based model solving the differential equation, I give somehow an approximate model that more or less does as well as that, but it is cheap to compute. Okay, so typically in complex problems such as monsoon prediction, where you don't have the actual physics or you cannot incorporate all the physics, I'll give some more details in the next slide. Okay, in such cases we use surrogate models, and these are popularly used in design. And one of the popular tools used for surrogate models is our neural networks and machine learning. Okay. Another thing, as I said earlier on in this class, we have a design and optimization problem. Can you find out parameters that result in maximum heat transfer or minimum heat transfer? Once again, you can use surrogate models there in order to figure this out. Finally, we can use data-based models to solve inverse problems, as we will see later on in this course. Okay. So this is basically our major concentration in this course, but in between you will see that we need surrogate models just to go back there. Okay. So if we come back to our example, our old example of our fin, I think with this data or something close to this data, Professor Balaji would have done this earlier on in the course. So we measure the temperatures at these 4 points. The experimental temperature is this. The question is, find out the fin parameter m. Okay, this is the standard inverse problem. Forward problem is, given m, find out temperatures. Inverse problem is, given temperatures, find m. A physics-based forward model would be, we solve the differential equation, we get this relationship, and then we use some regression technique. Okay, you could take a log and use linear regression, or you could use non-linear regression. But here is the problem. What if we don't know this? Now you might say, this is a very simple problem. Obviously know this. So obviously this is a toy problem, but I could make this a more complex problem. Just to give you a small perturbation on this case, suppose I make this a little bit thick and I make the shape a little bit weird, you will see that you cannot actually give, at the very least, you can't give me an analytical model. We can also have more complex cases where we might need data instead of physics. Here are some of these scenarios. You don't know the forward model completely. For example, weather prediction, we actually don't know the full model for the weather. Okay, we actually don't even know what all things contribute to the weather. Okay? Some of you who are doing the atmospheric sciences course, you will know this. We know a certain amount of things that contribute to the weather, but we do not know all the parameters. Similarly, climate modeling, okay, we do not know. Or you have an analytical model such as the turbulent Navier-Stokes equation, the full Navier-Stokes equations, but there is no single analytical solution that you can give for it. For example, we would need complex turbulence models which are still not completely known by themselves. Just to distinguish between these two cases, here we don't even know what all factors contribute. Here we know all the factors that contribute, but nonetheless we are not able to give them in a reasonably, even in a differential equation form, we are not able to give it. The third is where you know the all the parameters, you know all the terms in the differential equation, but it is computationally expensive. So for example, even if I take the simple case of conduction with heat generation in a complex 3D geometry, I can write down the Poisson or the Laplace equation, but you can't, you will have to solve it and it will be expensive, computationally expensive to solve it each time. In all these cases, we can use prior data in order to make a surrogate or a simpler model of the physics that works approximately as well, but is much faster. Okay. So in the absence of forward models, we need a technique that can satisfy some properties. Okay. So what are these properties? It should be able to approximate even fairly complex functions. Okay. What I mean by fairly complex functions is, so suppose I take a 1D case, okay, and I say my function will be a polynomial. But if I have functions looking like this, it's very hard for polynomials to approximate functions of that sort. Okay. Second thing, a desired thing for a forward model is that as you increase the number of data examples that you give to it. Now I have kind of jumped to this data example. What I mean by this whole thing, which we will emphasize again and again over the next couple of classes, it is this. Now notice when I am doing this fin case, this is my final data. What I would actually require to give in terms of creating a model is lots of fins of different types measured at different points with different m's, and I am giving you q. So I'll give you some q1 and some set of parameters m1, x1, etc. Then some other person. So you can think of this as follows. Let us say that multiple people throughout the world have been measuring this for a long time, and somehow we happen to grab this data set. Okay, so this could be q2, m2, x2, etc., q3, m3, x3. Like this, somebody gives you thousands of data points and says, okay, I can't tell you what the physics is, but I know that for this m and this x, I got this q. For this m and this x, I got this q. Again, to give you a monsoon example, or a very, very simplified example, suppose temperature and humidity over the last 10 years data, you also know all the rainfall data. Then given the temperature and humidity over the last month, can you predict rainfall for this month? Okay, something of that sort. So a data example is this. This is what is meant by a data example. That is sets of prior data that we have collected for this sort of problem, out of which we want to say or create a forward model, which is based on simply data rather than saying that I know something a little bit about physics. Okay. We will see later on this course something called a physics informed neural network that incorporates both prior data as well as physics in the problem. Incidentally, this is what is called learning in the machine learning literature. What is learning? Again, I'll give you like greater detail, both probably a little bit today and a little bit on in the next class. So what we do is, as you keep on increasing the number of these things, its prediction should get better and better. Okay, that is when it's said that you are learning. You have seen more examples, you are going to give me better answers. Okay. Finally, as I increase the number of parameters in the model, it should more and more approach the actual. So that is, your approximation should get better even with the number of parameters. This will become clearer as I come to neural networks and other things probably in the next class. Okay. So there is one such technique which satisfies all this, or one such approach which satisfies all this, and these are what are called as neural networks. Okay. You would have seen this picture, and the general explanation is that this is similar to the structure in our brain. Now we know that this is far, far, far away from anything that our brain actually does. But the original inspiration for neural networks was based on the structure of the neurons in our brain, but they really, really, really abstracted it. Okay, so it's really far away from how the brain actually works, but in a very simplified sense, a very, very simplified model. It's sort of like, I mean, it's like saying that this is a man. Okay, it's a cartoon picture of a brain. Okay, so very, very simple idea, but we will go into greater details in this in the next few classes. Okay. Now, the way we are going to look at neural networks is that they are a function approximation technique. So that is the approach we are going to take as far as this class goes. And I would recommend, if those of you who are, I have done, in my group and even otherwise in collaborations, a large number of problems in a large number of fields using neural networks. And this kind of perspective that it's a function approximation technique is always a very useful perspective. Okay, so regardless of what problem you are doing. Okay, the neural network satisfies something called the universal approximation theorem. Again, I'll briefly introduce you to this even later on, but I'll just give you a big picture, hand waving picture, which is like this. You see, what it says is that it can approximate any function, regardless of what function you give me, as long as I know the inputs and the output of that function. Okay, I can approximate any function to arbitrary accuracy, provided you give me sufficient number of knobs. And this will become clearer as we go on further. Okay. Finally, they can learn. As you give more and more examples, neural networks will get better and better at approximating the original function. Okay. There are two ways in which ANNs are connected to inverse methods. The physics model in the forward problem can be approximated. That is, we can create a data model or a surrogate model for the forward problem using an ANN. Okay. So solving an inverse problem, okay, would require you to do an ANN. Another thing is that the parameters of the neural network need to be solved again as a inverse problem. This will be a little bit confusing when I say it first, but it is ironic that in order to solve a inverse problem, you need a neural network, and in order to find out which neural network it is, you will have to solve another inverse problem. So inverse requires ANN, and ANN will require another inverse problem. Okay. So in fact, if you see a neural network literature, you will find things like, I use Liebenberg-Marquardt in order to solve the neural network, which you are already familiar with. So it is really a sort of a symbiotic relationship between solving an inverse problem and solving neural networks. So all that you have learned so far in the course is not only useful for you for solving general inverse problems, it's also useful for you should you actually go ahead and study machine learning somewhere else, because effectively we'll be solving inverse problems even in machine learning. Okay. So there are various types of neural networks. Three of the most popular ones are, like I said, artificial neural networks. I am kind of abusing the term. I am going to do something called multi-layer perceptrons, but I am just simply going to call it artificial neural networks. For typically numerical data of the sort of heat transfer problems that we are doing, these are the best type of networks. There are something called convolutional neural networks, These are good for image-based data. Is this a cat? Is this a dog? Your Google Pixel, Facebook identification, everything uses something called convolutional neural networks. Recurrent neural networks are for time-dependent data. Even when I'm speaking, you see YouTube, when it does our speech translation, some of you might have seen it, not speech translation uses this, but speech transcription. When I say a word, it gives you closed captions. Okay, so all that uses recurrent neural networks. So we'll take just sort of a review. It's also a good check for me if everything is working at your end. Could you please go to this website, itempool.com. You should be able to see this on your screens. Rajesh, maybe you could type this on the chat, itempool.com/Balaji/live. Uh, Please try going there. Yeah, please go there. I will also wait till got a reasonable number of answers.
But we have to fill that, sir.
Yeah. Just fill them here.
Is it survey or something?
It's not a survey. I am just asking some questions. Assume this is like a quiz. Of course, I am not collecting anybody's name or anything. Okay, about 55 people have answered. So just one more minute and I will stop this and we can go to the. Okay, so what this is showing is like about 46 people have given the same answer, and then there are other people who have given slightly different answers. Yeah, so just stop here. Yeah, so you have written analytical. Analytical is fine. Statistical is not quite accurate. So the first thing is physics-based models. So traditional models, we are using physics-based models. Whereas for machine learning based models, we basically base it on prior data. Okay. So people have given some variations of this, but I think posterior data is not true for, let's say, for physics. Um, I don't know if it shows both the answers. So the next question should be going live. Please see it and answer. This is a multiple choice question. You can correct all the things that you think are right. Okay, so multiple choices may be correct. You're able to see it, right? Yeah. Okay. Okay. Just one more minute. About 60 people have answered this. Okay, I'll just okay. So some people have said A, that is not true. So neural networks don't model in great detail how our brain works. It's kind of like I said, it's sort of a cartoon picture. And as we come to neural networks, you will see that they are very far away from even whatever little idea we have about how our own brains work. You will see that they are not like that at all. But they are function approximators. Okay, I see that most people have got that right and a few people have not written the others. So I just want to explain. So they do approximate, they are essentially neural networks, as you'll see later on, are essentially just a graphical way of representing a complex function. Okay, that is one way to see neural networks. They have a lot of parameters that need to be tuned. As I said, as you increase the number of parameters, you get better tuning. Okay, they obey something called the universal approximation theorem, okay, which says that under certain conditions, which says that a neural network can approximate any function whatsoever, okay, provided you give me sufficient number of parameters, okay, and you give me sufficient data, I'll be able to do that. Okay, so final question for this session. So the question is, I had talked about something called surrogate models. Once again, mark all that applies to surrogate models. right? Okay. So some people, so just to clarify, surrogate models are never more accurate than physics-based forward models. They are always, because we actually create surrogate models in order to approximate physics-based models, as you will see when we go on later on in the course. Okay. We actually take a physics-based model. The physics-based model might be based on physics, or that is differential equation, or based on actual experiments. But in any case, a surrogate model is simply a data-based model, which is less accurate than whatever happens in actual physics. But the reason we are happy with going with less accuracy is because we want to make sure that it is faster. Okay. So that is the whole point typically of a surrogate model, that they are typically faster than physics-based models. In rare occasions, I mean very rare occasions, they might be slow, but I actually do not know any actual case where they'll be slow or people would be happy with that. In that case, you might as well use a physics-based model. So the major reason for using a surrogate model is that they are faster, but they are less accurate. Okay. And a standard, since we now know that a neural network can approximate any function, the basic idea behind using neural networks is that it can be a universal surrogate model for any sort of physics, because I can approximate any function. The only question then becomes, can you make it faster than the actual physics model? Okay. So we see that. One second. So the topics that we'll be covering in the rest of the course are basics of neural networks. The linear regression that you did, we will repose it sort of as a machine learning algorithm. And I'll give you a brief introduction to somebody had actually written logistic regression somewhere here. The reason I am doing logistic regression is because it gives you a natural segue into neural networks. And within neural networks, there is an algorithm called backpropagation, which is what makes it practical for us to find out these parameters. And backpropagation essentially is related to I told you that we need to solve an inverse problem in order to find out the parameters of the neural network. So backpropagation is part of finding out those parameters. Okay. And we will, of course, apply neural networks for inverse problems. And finally, I'll cover something called physics-informed neural networks for inverse problems. This is a very recent technique where we even use the governing equations as if they are data. Okay, so this is basically what I'll be covering. Earlier on, last year and the year before that, I covered a little bit of convolutional neural networks, but their direct application to inverse problems has been very little. So in all probability, I would spend more time in physics-informed neural networks, because especially for people here, it might be extremely useful. Okay. Whether you are going to the industry or you are going for higher studies, physics-informed neural networks are right now a hot area. So I suspect that they'll be more useful than convolutional neural networks for you. So that is the plan for the rest of the course.
Hello, sir.
Yeah.
In previously, we have told that there are a lot of parameters to tune in neural networks, right?
Yes.
But these parameters are learned, right? Not tuned. Only few parameters are tuned, right? Like learning rate and
Being
all.
learned. Both in my terminology, tuned and learned mean the same thing.
Okay.
Okay, they are tuned according to the examples that you give, or they are learned according to the examples that you give. So you give some examples and we learn those parameters. Just like linear regression, you give some data points, and based on that, you give some optimal parameters, right? You give some optimal A and B. So similarly for neural networks, based on the examples that the data set that we have given, we learn some parameters. So you can call it tune-in, you can call it learning. Both are the same.
Do we use a Bayesian approach also in neural network?
We can do that. We can do that. I'll, if time permits, I'll give you an example of doing that also. Actually, I'll give you an example of using neural networks within Bayesian rather than anything else. But yeah, you can have we do have a Bayesian approach. These are called Bayesian nets. It's a good question. We do have a Bayesian approach for neural networks also.
So
Slightly
we
more
will be
complex.
covering it, sir.
No, we will probably not be covering it. That's probably a little bit too involved. But the ideas that you used earlier are actually directly usable here too. It's just computationally a little bit involved.
Thank you, sir.
Any other questions? Okay, if not, thank you. Happy New Year to everybody. Please stay safe.